Hello everyone, today I will be presenting the paper Fast and Exact Convex Hull Simplification. Now I will talk about the problem definitions. So first let CH of P be the convex hull of all points in P. And computing the convex hull is a fundamental problem in computational geometry. And also finding subsets to minimize some cost function of QP is also well studied. And I'll start by introducing the definition of the cost that we use. Now the cost of two sets Q and P is defined by looking at the convex hull of Q, and for all points in P which are outside that hull of Q, we compute their distance to that hull of Q. Now, out of all such distances, we pick the maximum and call it cost of QP. Now this is essentially the Hausdorff distance between the convex hull of Q and the convex hull of P, when Q is a subset of P. Now on the figure, vertex marked red is the maximum distance to the hull of Q, whose points are marked blue, so the distance is our cost. Now, using that cost, we define two versions of the problem. So in the first version, called min epsilon version, we are given a set P of points in the plane and some integer k. Our task is to select the subset Q of P such that cost of Q and P is minimized. Now, in the second version, called min k version, we are also given a set P of points in the plane, but instead of k, we are given epsilon, and our task is to select the subset with minimum cardinality, such that its cost is bounded by epsilon. Now, we can also consider the same problem, but restrict the given point set P to be in the convex position. And notice that in the convex position, we get a natural ordering of points by sorting them around any point inside their convex hull. Now this will give us another two versions of the problem, for a total of 4 versions. Now we will show subcubic algorithms for general case and near linear time algorithms for the convex case. Now also we can view the convex position case as simplifying some polygon. Now I will discuss prior and related work for our problems. So a very similar topic is coarse set studies, where the subset is selected such that it preserves some geometry of the given set of points. So if by width of U and P we define the difference between the max of the dot products between U and all points in P and the mean of the dot products between U and all points in P, then some subset Q of P is an epsilon kernel if 1 minus epsilon times the width of U and P is at most width of U and Q. Now, a paper called Approximating Extent Measures of Points showed that in d dimensions, an epsilon kernel of size order of 1 over epsilon to the power of d minus 1 over 2 exists. Then a paper called Minimum Coarse Sets for Maximal Representation of Multidimensional Data showed that the smallest epsilon coarse set in the plane can be found in cubic time if we use the max of the dot products of U and all points in P as the width of U and P. It should be noted that those results are not exactly the same as the Hausdorff distance results. Now also some problems where Q does not have to be a subset of P have been considered. So a paper called Finding Minimal Convex Nested Polygons considered a problem where we are given two convex polygons where one is contained inside the other one. Now the problem is to find a convex polygon with minimum number of vertices such that it is contained between two given polygons. Now also the paper called Hausdorff approximation of convex polygons considered a problem where we are given some set P in the convex position and the starting vertex on its convex hull boundary. The paper considers the versions of the problem where we either minimize the amount of points or minimize the cost. It gave near linear time algorithms for those problems. It also showed that by applying the results to the case where the starting point is not given, we'll solve the problem with at most one extra vertex. Now furthermore, simplifying polygons and polygonal chain is a very similar problem. And while the discussed results are very similar to the problems that we are studying, each of them differs in some key way. Now I will briefly summarize the results that we get in this paper. So first we get the n log squared n time algorithm for the min k version of the problem when the given points are restricted to be in the convex position. Next we get the min epsilon algorithm, which will with high probability work in n log cubed n time. Here c is any constant greater than 1. For the general case, we reduce our problems to the all pairs shortest path problem on directed advented graphs, and we solve our problems in the time n to the 2.532, which is essentially the time to solve all pairs shortest paths on directed unweighted graphs. And we also get a slightly faster version for min epsilon algorithm for small k by solving a slightly different graph problem, and it works in kn to the 2.376 time. Now, while most of our paper is focused on exact results, we also mention some approximation results, which we get by applying the algorithms for the convex case to the general case. More specifically, we take the convex hull of the given points and ignore any points inside the convex hull. This will result in at most twice points selected in the subset as in the optimal solution picked by the algorithm. Now, also, instead of looking at all pairs shortest paths for the general case for our graph problems, we can look at the single source shortest path. This can lead to n squared log n time algorithm for both min k and min epsilon version, but will result in one extra point in the selected subset. Now I want to talk about the intuition for the min k algorithm for the version of the problem where the points are in the convex position. And first I want to talk about how the cost of the convex hull can be decomposed, meaning that it can be represented in terms of the individual edge costs. And for that we notice that the points between the endpoints of any edge would project to that edge. So we define the cost zero function, which is defined in terms of point indices, and recall that the points are indexed according to the clockwise order of points. And here, cost zero of ij is the maximum distance between the edge ij and any point I and before point j in the clockwise order. And this basically means that the cost of the any hull would be written as the maximum of individual edge costs. Another important observation is that we can be greedy when selecting the points. If we fix any vertex and move another one close the clockwise order, cost would monotonically increase. This means that once we exceed epsilon, we know that for all vertices further along the clockwise order, cost would keep exceeding epsilon. Also notice that picking an earlier vertex could result in a smaller cost overall for the whole, but for the min k version of the problem, we are not minimizing the cost, we are only requiring that the cost does not exceed some given epsilon. Now I will start describing the min k version of the algorithm, where the points are restricted to be in the convex position. And first I will introduce some definitions. We will start with f epsilon of I, which is a function from a vertex index to a vertex index, and we call f epsilon of I the friend value of I. And it would just be the furthest index in the clockwise ordering, such that the cost of the edge between I and f epsilon of I does not exceed epsilon. Now, for any I, f epsilon of I is equal to I, then the point pi in the solution. So we check for that with the preprocessing step and assume that f epsilon of I is not equal to I. Now we define a grid sequence to be the increasing sequence of indices, which are iterations of f of epsilon. So if we start at any index and keep applying f epsilon to it, then as long as it is increasing, we get a greedy sequence. We also require that the friend of the last index, the sequence, is smaller than the last index, so that the sequence does not wrap around from higher indices to lower indices. This means that we take as many points as we can as long as indices are increasing. Now, we also define the greedy sequence to be valid. If pipeline f epsilon to the last index in the sequence, we get a result which is at least as large as the first index in the sequence. And we prove that any valid greedy sequence of minimum possible cardinality would be the optimal solution to the problem. And here is how we solve the problem once we know all f epsilon values, which we haven't yet shown how to compute, but assuming that we have such values, we define a directed graphs with vertices p in the points in P and edges such that there is an edge from Pi to Pj if j is a friend of I and j is bigger than I. Now this graph is acyclic because we only have edges from lower indices to higher indices, and our degree of each vertex is 1 because we only have one friend for each vertex. Now this means that this graph would be a forest and its sinks would be the roots of the trees in it. And any path that ends in sink corresponds to a greedy sequence. The actual algorithm, we first construct the graph. Now we need to list all possible greedy sequences which are vertex in the graph. And we can get all those pairs by topologically sorting the graph. And we only have a linear number of them, as we only have one vertex sink per vertex. Now then for all such pairs, we only need to select the ones corresponding to valid greedy sequences. And we can do that by checking if f epsilon applied to sink index is larger than the vertex index. Now then we need to find the minimum length path, which we can do by looking at the depth of each vertex in the tree. So we can do those operations in linear time. So what remains to get the answer is to compute the f epsilon values for all vertices. To compute the f epsilon values, use the following result from the paper called Farthest Point Queries with geometric and combinatorial constraints. I will not go into the details of the results, but with some additional work we can get log squared n query time for cost 0 values if we do the n log n precomputation. And this allows us to compute f epsilon values by doing a linear number of cost 0 queries. So to achieve this, we can use two iterators I and j, which follow clockwise ordering of points where I corresponds to the index of the vertex for which we compute the friend value, and j moves until cost 0 find j exceeds f epsilon. Shows that j does not need to go counterclockwise, and even when we increase I. In other words, after we find the friend value of I, we do not need to start searching from I plus 1 again for the friend value of I plus 1. So this means that we get the linear number of changes to I and j, and we get the linear number of queries. And overall, the friend values can be computed in n log squared n time. And this ends up being the bottleneck for our computations. So overall, it would give us the n log squared n time for the min k algorithm for the convex version of the problem. Now I will explain how to use the discussed min k algorithm to get the randomized min epsilon algorithm when the points are restricted to be in the convex position. So given any epsilon value, we define the decision procedure, which we call the decider of epsilon. Now in this procedure, we need to decide if a min k algorithm would have at most k points in the solution. So we use the min k algorithm as a black box. And with this we can search over the possible set of epsilon values. Now recall that for this problem, the cost of the solution whole is the max of the cost of its edges. So possible values for epsilon are just the possible values of edge costs. And we only have n squared possibility for edges. So we have n squared possibilities for edge costs. So to solve the problem, we can compute the set epsilon, sort it, and search over it using our decision procedure, but it would end up giving us quadratic time, and the size of the set is quadratic. So instead we use the sampling procedure to reduce the search space, and we apply the procedure similar to the one shown in the paper called the fresh rate distance revisited and extended. Now for sampling, recall that we could compute cost zero values in log squared n time as long as we did the n log n precomputation. So we essentially sample epsilon values in the same time, as all we need is to compute the cost zero values. If we sample from the set of epsilon values, we may miss the true answer, but it still allows us to limit our search range. If we sort a sample, then we can find the values where the decider switches between true and false. And now we need some way to get all values between those two values. And we use the procedure called extract, which will output a list of those values. Now, I will not go into the details, but this list can be computed in n log cubed n plus x log squared n time. So our runtime would depend on the side of this list x. And if our sample size is 4n, then for any constant c greater than 1, the probability that the size of x will be bigger than c and log n is very small. It is smaller than 1 over n to the c. So to do the algorithm, the first step is to do all the precomputations, such as sorting the points and doing the precomputation for cost queries. Then we sample for n values, sort them, and search over them using the decider procedure. And this will give us the range alpha beta. We can then use the extract procedure on that range alpha beta to get the values between alpha and beta. And finally, we can search again over those values using the decider procedure to get the true answer to our problem. Notice that as we have seen before, the size of x is n log n with a high probability. So with probability 1 minus 1 over n to the c, the algorithm takes order of cn log cubed n time. But even in the worst case, the running time would only be n squared log squared n. Now we talk about the versions of the problem where the points are not required to be in the convex position. And to solve the min k version, reduce it to a graph problem and apply all pairs shortest path algorithm on directed unweighted graphs. And to convert the problem to a graph problem, use the approach similar to the one used in the paper called sparse convex hole coverage. And first, by HL of AB, we define the half space to the left of the directed H, AB. And for such directed wedge, we define its weight to be the maximum distance from all points that lie in that half space HL of AB to the HAB. And this gives us a complete directed graph. And we show that all H weights can be precomputed in n squared log n time. To get the solution for the min k version of the problem for the general case, just need to find the cycle with minimum cardinality in our graph such that all edges in that cycle are bounded by epsilon. So given any epsilon, we remove all edges with weights larger than epsilon. After we do that, we can ignore the remaining edge weights because they are all smaller than or equal to epsilon. This means that we are left with a directed unweighted graph, and to find the minimum cardinality cycle, we can apply the all pairs shortest path algorithm to it, and then check all pairs for forming a cycle. For the all pairs shortest path algorithm, We use the result from the paper called all pairs shortest path using bridging sets and rectangular matrix multiplication. And the result is that all pairs shortest path problem on directed unweighted graphs can be solved in time into the 2.5302. So our problem can be solved in that time as well, because all pairs shortest path subroutine is our bottleneck. To solve the min epsilon version of the problem for the general case, we use the approach similar to how we approach the min epsilon version for the convex case, because cost is also decomposable as the max of edge weight values. Now, since there are n squared different edge weight values, we end up having n squared different epsilon values. So we can compute, sort, and search over them using the min case solution as a black box, as we did in the convex version. Now, the difference is that n squared is no longer the bottleneck, so we do not need to sample. Now, this means that the running time is essentially the same as the other problem, except for a log factor, and it is the time to solve the all pairs shortest path problem on directed and weighted graphs. Now, this gives us n to the 2.532 time to solve the min epsilon version of the problem. And if k is small, we can slightly improve the running time. Now, the paper called on the exponent of the all pairs shortest path problem shows that we can solve the all pairs shortest path problem, where path lengths are bounded by k is approximately kn to the 2.376 time, which means that we can solve the min epsilon version of our problem in kn to the 2.376 time. Thank you for listening to our presentation.